right, section 1.2, graphs of equations. Solutions! Those are the ones that work, right? So if they work, what kind of statement must we have? So easy? It might be hard. Yeah, it's a true statement. Solution just ends in a true statement. No big deal. So if you wanted to check a point, let's say that you're not solving. And this could actually be for like an equation in the future that you can't solve, at least not by algebraic means. How do you check to make sure something actually works? Plug it in, right? And hopefully using proper PEMDAS and proper notation, you will multiply first before subtracting. You will write the right numbers down. Smartboard makes me dumb sometimes. How do you show it's a solution? Ooh, yeah, it's a solution. Why? It's true. In math, do you ever get an answer that you think should be right, but when you plug it in, it's false? Yes. No way, really? It's called an inconsistent solution. Sometimes by doing math, by doing our algebraic procedures, especially like squaring a square root, sometimes we make the impossible possible, but it really is still impossible. Don't worry, you can't talk about it when it comes. That's the helpful thing to be able to make sure your answers really are answers. Do you have to check every single problem? Not necessarily. But keep an eye open sometimes. The math tells you one thing, but your logic hopefully will lead you to understanding that it's not actually a true solution. Sketching graphs. Wait, are you serious? This is like Algebra 1. What's Algebra 1? Tables. And some of you are like, no, we're in Precalc. We shouldn't have to go back to tables. Maybe that's true. But to be honest, sometimes it's not. And it's better to make a table than to be totally stuck. Just a few of you, as you were writing, are like, this is dumb. I'll just use my calculator. But what if it's a test or quiz without your calculator?
Let me see. Just a format question. What do you write, like, kind of keywords in the left?
It's called Cornell Notes, bud. It's a way of setting up notes such that important terms are separate. So that way, as you look through a section, you can kind of point out the big ideas, and then everything on the inside is like all the explanation.
Do you want us to write explanation there also, like Mr. Crawford did last year?
Oh, like extra answering questions?
Yeah, like he had the vocabulary and what he meant in the left column also.
Oh, and what it meant as well. I put most of the details on the right. I don't put as much over here. However, in Cornell, it's not a bad idea, and he might have taught this last year. When you're going back over your notes, that should be a thing, right, to make sure you understand. You can write questions out there in like a different color, and then you have it to ask the next day and maybe get answered. So that's a good thing maybe to put out there also. But I'll put explanations, Luca, on this side along with examples. I didn't realize he and I applied differently. Did he do still the essential question at the end? You had to go home and like answer an extra question. That's really good. We just always run out of time. So I don't really do that either. Now I want you guys to double underline last resort. What does that mean? It's only if you need to. And technically, what should be your last resort if it's a problem where you're not supposed to be using your calculator? Your calculator is your last resort. And if you can't use it on a test, well, that's not a very helpful last resort. But guys, looking down below, as you're going through, you're going to get to this example. And all I'm asking you is look at these 4 equations, these 4 functions, and basically pick out the ones that might be good candidates for point plotting. Which ones might throw you for a loop? The lines? Hopefully not, right? We are going to be able to deal with simple functions, hopefully, and not need to use this as a last resort. But what's weird with him?
It doesn't have a third trinomial.
Yeah, it doesn't have a third term. And it's not factored nice, right? Now, could you do stuff with this function? Yeah, and we're going to talk about that, how to find the zeros and the intercepts, and even how to think about symmetry and blah, 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 blah. Complete the square. Well, that's fun. But for right now, table could be one way of dealing with it if you needed to, if you needed a graph. Same thing with, right, square root of x squared minus 6. Don't think we've memorized that one before, right? Worst comes to worst. Now just remind me real quick, how do you make a table? Besides just writing x, y?
You have to choose a point.
You got to pick some points. And you got to pick enough points to try to figure out what the shape is. Maybe more than 2 or 3, maybe more like 5 or 6. But it is a strategy, okay? It is a strategy. Just want to remind you guys of that. It's not too basic. It's not too elementary. It's not dumb to use a table if you can't deal with it any other way.
Why did you cross those ones off again?
Because they're lines, so hopefully intercept slopes will be able to graph those quickly without having to resort to just like guessing points.
Because there's a number in front of the x.
Or we can also, remember, we can think about it as, and we haven't talked about it yet, Kristen. But we can do our intercept, and then down to over 1. We can get a graph pretty quickly without having to worry. You know what I mean? So there are functions that are going to fit into nice little, like, formulate patterns, and we can just deal with them real fast and get a nice graph. But there are ones that are going to be unique that point plotting could be a way of dealing with them. Okay. What if, though, even for complicated ones, we do need a graph? There are some strategies. That's what I was just starting to say. There are some strategies that we can use. Ones that you guys have seen before, for the most part. A few that might be a little bit new. And ones that you might still hate, like symmetry. So technically, the two most fundamental clues for graphing any function given to you, sometimes it's easier, sometimes it's harder, are intercepts and symmetry. Nice thing is, last night in homework, you already started talking about x and y intercepts because they asked about, hey, if there's a point on the x-axis, what's always true? If there's a point on the y-axis, what's always true? So help me out, fill it in. A point on the x-axis, what's always true? The y is always 0, right? Now, who knows what this one's going to be? Let's make it like letter A. I don't know. Could be 2 over, 5 over, or 10 over, depending on the scale of the graph, right? But we do know that we can always set y equal to 0 and solve for, well, what's the one variable left if it's a normal y and x equation? The other. Now be careful though. The x-intercept isn't just an x value. The x-intercept is the entire point with the x value that you solve for and the y equals 0. It's the ordered pair, right? It's the entire thing. Something silly that frequently kind of get messed up. And then similarly, y-intercepts. What did you guys write down in homework last night? X is always 0. If you guys finish writing this, I want you to ponder a question. Which one is almost always, for normal functions, the easiest one to solve for between these two?
For x. Because sometimes you have like y equals x to the third.
So then, if we think about it, there were 2 different answers. Let's look at an example and then test out your hypothesis. Test it out. Some of you said, no, it's way easier to plug in x as 0. So you're like, no, plug in y as 0. Solve for x. That's easiest. Okay, then do one. Tell me which one was easier. If you can't see the function is y equals x cubed minus 4x. Can't see it. X cubed minus 4x. You can see some key points. Oh, that's lame. It's given to you. All right. So write down the ones, and then I want you to algebraically show me why. All right. You can steal it from the graph. But algebraically, how would you solve? How did you verify by using what we talked about? I'm just stealing the answers from the graph. You guys could do the same. But remember, I also want an algebraic proof, demonstration of why it is what it is. If you didn't have the graph, which is, to be honest, kind of the majority of pre-calc. Dealing with functions and just needing to understand how they move, how they work. Become more familiar with the different patterns. What if you didn't have the graph? X-intercept, plug in. Y is 0. Just a couple of you, maybe a few, maybe most, would add the 4x. Divide by x. X squared is equal to 4. You might have just gotten one answer. Square root both sides and gotten x equals 2, but there are 3 answers. Some of you would have added the 4x divided by x. You would have gotten something like 4 equals x squared. You would have plus or minus square rooted and been like, haha, there are 2 answers, but there are 3. How must you approach a polynomial set equal to 0 every single time? Factor. I know. Some of you love algebra. You're like, move and then divide and then get rid of stuff. But the problem is when you get rid of stuff, you get rid of answers. Whenever you're getting rid of variables. But when you factor and set each factor equal to 0, can we get x equals 0? Yep. Can we get x equals negative 2? Yep. Can we get x equals positive 2? The only way we can get all 3. We must factor. Now, y-intercept, remember, just plug and chug, right? Plug it in. Technically, PEMDAS would say, do the power first, 0 to any power is still 0, 4 times 0, now do multiplication is 0, and then the subtraction is 0. Which one's easier? X-intercept or y-intercept?
Way.
Oh, yeah. All day long. We like this one better. We can put like a little happy face by him because he's fun. Take away a happy face because he's scary. But either way, we don't mind him. The trouble comes with x-intercept, and just throw a log in there. Throw an e to the power of in there. Throw a sign in there. Oh, it gets rough. So even though it's basic, can it be complicated to actually do? Right, fine? Yeah. It's true. But we'll hang in there together, okay? Got it? Going. All right. Symmetry. This one's rough. This one I've Calc BC kids. They've already gotten through probably honors pre-cal and then Calc AB and now they're in Calc BC. And they're still like, wait, what's it mean again? It's okay, that was you guys in the distance formula earlier. But symmetry, it's not easy. It's not hard either. We'll get into more detail for each of these. For right now, I'm just going to show you equations that have the given symmetries and why, according to the clues that are up there, or how, according to the clues that are up there, we can tell. I'll give you a second, though, to get that first one. So I'm going to put a graph in just one. An equation. In just 1 second. There's technically a table on the next page from the book that goes into all this detail, but I think this is a good summary. to 3 functions that have each of the given symmetries. I'm going to show you why, according to the clue, it's true.
You know what it looks for me?
Huh.
In my opinion, that you're reflecting across the x-axis, like.
Oh, how it looks?
Yeah.
I'll do it after I test. But yeah, I'll show sketching.
Okay.
Hold on. You guys notice what's different? A negative y. So I plug in and say, what happens if I plug in a negative y? What happens? Nothing. It's just the same. Has x-axis symmetry. What does it look like? It's a sideways parabola. It flips across. You could fold it across the x-axis and it'd be the same. Y equals x squared. What's different and yet it better stay the same? Negative x. Y equals negative x squared. It's a negative, but it doesn't change anything. Has y-axis symmetry. What does it look like? Does that make sense? Fold it across the y. Stays the same. Has that symmetry like a butterfly. You could fold it and it'd be the same. Origin symmetry. Negative x and a negative y. Plug in a negative y. Plug in a negative x. Simplify. What's a negative cubed? Negative. It's different. No, it's not. Multiply or divide both sides by negative. What's it look like? Origin's the funny one. If you fold it across and down, it would be the same. If you fold it over and down, across the y and across the x.
So it is a reflection.
But we're not actually reflecting. It's like in its nature, it has that symmetry across. Across the x, across the y, and across the one.
It's like mirroring.
Yeah, that makes sense. Now, you guys saw 3 that it worked for, right? What worked for? Different tests. For x, you plug in a negative y and see if it stays the same. If not, no x-axis symmetry. For y-axis, plug in a negative x and see if it stays the same. But if it doesn't stay the same, no y-axis symmetry. So look at this one. Don't worry, the table, remember, it's the messy. You can read it in the book. It's great. I like mine better. Look at him. If you plug in a negative y, is the negative going to go away when you simplify? It's going to stay. So x-axis symmetry. No way, Jose. If I plug in a negative x, ooh, that looks helpful. Or hopeful. Y-axis symmetry, I would plug in a negative x. Ooh, what happens? Negative squared is a, does it have y-axis symmetry? Yes. You could try origin. But for origin, plugging in a negative y and plugging in a negative x, you would still have the negative y, but the x would, same, different. Did that work? The only symmetry it has is y-axis. Now pause, wait. I'm going to grab your Sudokus as you walk out the door for nutrition. And pause, wait. Homework, due tomorrow. But what if we didn't finish? We basically did. The one thing we didn't do is write down a snazzy formula for a circle that you've seen before. It's in your book. You can find it. It's on the notes online. You guys are good to go. Homework due tomorrow, okay? Sudoku. Give it to me and I'll out. Bye, guys.